Hello viewer, you are watching Elim TV. Welcome to Form 2 Physics, lesson 3. The topic is magnetism, and today we want to narrow our discussion to domain theory of magnetism. So I'm your teacher, Benjamin K. Makanda, and I hope you're going to enjoy the lesson. Before we start our lesson, you may be having questions, comments, compliments. You can get us on SMS 40007. You can also call on 0726 842 644. You can also use our Facebook page, Elim TV, and Twitter account at Elim_KE. So I hope you're going to be there and have a pen and a paper to follow up on this lesson. Now, let's begin by looking at the specific objectives of the lesson. And by the end of this lesson, the learner should be able to explain the domain theory of magnetism. So you only have one key objective that you have to achieve by the end of this lesson. So once we are done with everything within this lesson, then you as a learner should be able to explain the domain theory of magnetism. Having understood what domain theory is, you'll be able now to explain this. Now, lesson preview. We want to look at shortly at review of lesson 2. Explain the domain theory of magnetism, which is our main discussion of the day. Then we are going to look at questions that relate to our discussion. So before we move on to our today's discussion, let's first of all review our lesson number 2. In lesson 2, what did we discuss? We looked at methods of magnetization and demagnetization, and some of the methods used to magnetize and demagnetize magnetic materials include electrical method, we have heating, we have high temperature, and many others including hammering. Those methods are the ones used to magnetize and demagnetize any magnetic materials. So we want to relate how these methods operate in actually understanding what domain theory of magnetism is. And to help us understand this, we want to shortly move to the lab and look at laboratory session, what we're going to discuss about the domain theory of magnetism. So let's have this in the lab. So we want to look at why magnetism passes through ions so well. What makes them pass through ions so well. So in a magnetic material is made up of zones. So looking at this diagram here, these zones are what we call the domains. The red and the green zones, they contain what we call the dipoles. Those are molecular magnets. We're using red, green, and blue, which are our molecular magnets. So these red, green, and blue, they are located in specific zones. So those zones are what we call the magnetic domains. So a magnet is made up of small magnetic molecules. So we have small magnetic molecules, which each molecule is having north and south pole. So all these ones, they have north and south pole. So when you use a compass needle and you keep on passing the compass needle around this magnetic material, then you note that the north-south poles of these magnets, they keep on deflecting in various zones, the zones you are calling the magnetic domains. So that when you put this one on an alternating current, the AC current, so when the current is moving up and down, the current moves in form of a wave, then the poles of the magnets keeps on changing because this current carries electricity, and the flow of the electric current also occasions the magnetic effect around it. So you realize that the domains in those areas, they are changing as the current changes. This alternating current keeps on changing, and therefore it also makes the domains to change. These domains contains the magnetic molecules called what? The dipoles. So they're actually moving around within their regions, as you're able to see here. So they keep on moving as the current continues to move. So if the current is stopped, they also stop moving. This gives us an indication that this moving current also causes an electric current. So let's look at the flow of the current and the pole with which this current comes with. Now, this is one of the zones. So we have a magnetic molecule here. So if we move that magnetic material, then the north poles are going to face away from it, while the south pole is close. Now we look at how this one happens in terms of magnetic field strength. then the magnetic field strength reduces with the distance. When the distance is reduced, what's going to happen to the magnetic field strength? You realize that the magnetic lines of force are going to be very, very close, and therefore this emerges virtually the same strength at the pole of that given magnet. So the poles are very strong, and therefore the magnetic strength is very, very strong. So magnetic field strength permeates easily through iron and emerges virtually. So let's summarize this observation. And a voltage causes electrons to flow. The second one is what we have here. We are now looking at how changing magnetic field or electric current also have an impact or not on the alignment of the magnetic molecules, the one we call the dipoles. So if we keep on changing from high to low, that one, the movement shows the flow of the current. When the flow of the current keeps on moving, the molecular magnet also changes. So the other theory we want to look at is the molecular theory of magnetism, and now we have a magnet. This magnet is just one magnet. When you take this magnet, magnets attract, that's one thing that we know. The unlike poles attract. What about the like poles? They repel, that's the repulsive force. So the like poles repel. So on the molecular theory of magnetism, we now borrow this property to help us understand. So a magnet is considered to be actually made up of small molecules. So when you take a piece of a magnet and you place it near iron filings, they are attracted. So you see they have been attracted. And then if you cut a magnetic material, this is a piece of a magnet, you make two other magnets of the same property. We had one, now I've just attained two other magnets with the same poles. So these two new magnets that have been made, they also attract, because they have poles, north and south pole. So meaning that a magnet, if we continue, then again we are not going to have four magnets here. We have just cut. So they again still have the same property, attractive property, repulsive property. So iron filings are being attracted. So those are the four pieces. So this cutting has something behind that we have to understand. We continue cutting these magnets into even smaller particles. Look at these particles that we are cutting. So these pieces of parts that we are cutting from the huge magnet are what we are calling the domains. So those domains are what we call the molecular magnets. So this is just a part of a huge magnet that we had, and it has an attractive property because it has attracted iron filings. Yeah. So it is just a fraction of the huge magnet that we had. So how can we call this kind of a piece? This one is called a magnetic domain or a dipole. A magnetic domain that actually houses a dipole. If you bring them together, they will still form a compact magnet. So we again get our original magnet. So we have to discuss this. What does this one mean? It means that if you cut a magnet, actually a magnet is made up of sub-magnetic materials called magnetic molecules. And each region within which these molecules are made is what we call the magnetic dipoles. Now, we have this tool here. We want to use it to understand what the magnetic theory or magnetic domain talks about. So we want to magnetize it. So look at the arrangement of the dipoles. The south-north poles are randomly arranged. Actually, they are randomly arranged such that within these big magnetic materials, they form a loop. So if we have it, then the arrangement within this material is in this form. So we start passing a magnet. When we pass the magnetic field lines, they are spreading the way you can see. They spread because they're using the north pole. This method of magnetization is called stroking. We are single stroking here or single touch. Then you realize that the randomly arranged dipoles are now aligned. Although not all of them are aligned, but to some extent, most of them are aligned. Then you continue passing the magnet. As you pass the magnetic lines of force even force the unaligned magnetic dipoles to get aligned. So at the end of it all the magnetic molecules within this material are now aligned and they are facing one direction. At this point, we say the magnet has attained maximum magnetism. So any magnet that attains maximum magnetism is said to be magnetic saturated. Because it is saturated, a saturation of the magnet, it means that even if we continue passing a magnet, it doesn't matter how strong that magnetic material is. All the dipoles and the magnetic molecules have already been aligned, and therefore the magnet is fully magnetized with the north pole, and then the rear end has the south pole. So this explanation or demonstration helps us understand what the domain theory talks about the magnetic dipole. So this end becomes the south pole from what we have just observed. So within this material, we have those molecules that have to be aligned in order for this material to become a magnetic material. Now, we experiment using it, and then you can see this material is also able to attract. Actually, this one is a ferromagnetic material. It has equality of poles. What do you mean by this? Poles have equal strength. Therefore, if we take a Bunsen burner and we hit this material at the middle, what's going to happen? The dipoles are going to be disarranged. They become non-aligned. Actually, they become disarranged, and therefore the material loses its magnetic. It becomes demagnetized. So the domain theory of magnetism. So let's understand what a domain is. A magnetic domain is a region in which the magnetic fields of atoms are grouped together and aligned. So the magnetic regions in which the magnetic fields of atoms, those atoms are called magnetic molecules. We also refer to them as the dipoles. The dipoles, these are the small molecular magnets where they are aligned. So different magnetic domains have different alignments. So if you move from magnetic domain A to magnetic domain B, the alignments are different. So magnetic domain is that region where the magnetic fields of atoms are grouped together and are aligned. To be aligned is actually to face in one specific direction. So that's about magnetic domain. The other thing that we need to know about the magnetic domain is that the magnetic domains are indicated by the arrows in the metal material. Now, let's look at one of the properties of the magnets. Magnets have polarity. Actually, magnets have poles. They have the north pole and the south pole. The fact that we have the north pole and the south pole, that one gives us an idea of direction. Therefore, when we want to indicate the magnetic domains or the magnetic molecules within the domains, we use arrows to indicate the direction of the magnetic line of force. And the magnetic line of force, as we're going to see later on, moves from the north pole to the south pole. That's why we are saying they are always indicated by the use of arrows within a given material. So the other thing that you have to understand about this is that you can't think of a magnetic domain as a miniature of magnets within a material. Actually, the molecules that resembles a magnet within a huge magnetic material, as we have seen. So we assume that a magnetic domain is a miniature of a magnet within a material that behave like a real magnet, because it's a small magnet, a subatomic magnet. So that if you continue cutting a big magnet, it gives these small magnets that still possess the same property that a big magnet has. So the domain theory explains this. So we have this description here. Suppose we are having an alternating current. That arrow is indicating the direction of the magnetic line of force. When the magnetic line of force keeps on changing, the blue is the north, the red is south. So when we change from north to south, also the direction of flow keeps on changing. That change in the magnetic line of force indicates that within a domain, when you actually perform if it is interfered with, then the arrangement of these subatomic particles are also likely to change. And if they change, then the alignment of the north-south direction also does change. So this demonstration helps us understand that. Again, still on the magnetic domain, what we can also be able to say about this is, in an magnetized object, like the initial piece of metal, all the magnetic domains are pointing in different directions. Any material that has not been magnetized, but is magnetic in nature, especially for magnetic materials, before it gets magnetized, the magnetic domains are actually pointing in different directions. Let's take a scenario of a class of 40 students. If we have these 40 students and 10 students to sit in class facing the board, 10 to sit in class facing back of the class, 10 of them, if it is possible, to sit facing the roof, and then the other ones should sit facing the floor. Then describe the arrangement or the seating pattern of the students. They are actually randomly seated. They are facing in various directions. So that arrangement of a class can actually be used to explain what a magnetized object looks like, because the magnetic domains are randomly arranged. They are actually facing in various directions. Now, when the metal becomes magnetized, which is what happens when it is rubbed with a strong magnet, all light magnetic poles get aligned. Now, at one point when a teacher comes to class, the students are asked, can you face the board? And all of them face the board. Then we say the students are attending. In this case, we say a material has been magnetized. Remember, in a class, not all students will face the board. Therefore, a magnetized material will also have part of the domains of the subatomic particles not aligned in one direction. Then we continue passing current in the same. And when we pass current in the same magnetized material, then we attain what we call magnetic saturation. Saturation is the state reached when an increase in applied external magnetic field cannot increase the magnetization of the material further. So you continue increasing the magnetic force to a material that has already been magnetized. It doesn't matter how many times you do it, but because all the dipoles have already been aligned, then the materials are not going to be aligned any further because they have reached the magnetic saturation. Now, the term saturation means that you can, if you continue adding more force to it, then the force is likely to do nothing. Just like you have a lot of sugar in tea, and then you keep on stirring the same tea, the sugar does not dissolve because the tea is saturated. A magnet also gets saturated at a point where all the dipoles or the molecules of the magnets have been aligned. That's what we call magnetic saturation. So from this explanation, there are three states of magnets. The first one is a magnetized state, where all the dipoles are randomly arranged. The second one is magnetized state, where up to 95% of the magnetic materials or the dipoles within the domains are aligned. Then the third one is the magnetic saturation, where all the dipoles have been aligned and further pass of electric current cannot actually make that material to change. So we call that one magnetic saturation. Just to again understand this, let's have this demonstration here. Yeah. So this one now summarize what magnetic saturation is. The first one is an unmagnetized state, domains randomly oriented. So the domains are randomly arranged. In the middle, we have magnetized state, domains oriented in external magnetic field. At least most of them are facing in a specific direction. Then the last one is the magnetic saturation, and then we call it a saturated state. And in this case, domains oriented strongly in an external magnetic field. All the domains and magnetic dipoles are aligned in one direction. So this one summarizes the behaviors of a magnetic material when a strong electric current is passed through, which help us understand the domain theory. Now, to further understand this, we have these diagrams here that will help us explain this. So in the first diagram, the diagram is actually showing us that the blue particles there, those ones are subatomic molecules or small magnets that have been cut from the main magnet, and therefore the magnetic lines of force are moving, showing that the material is magnetized. Then this one is a magnetic domains. Those magnetic domains, they have green arrows. Those green arrows actually indicate to us or shows us that those are the domains in which the dipoles are actually randomly arranged. The same applies to the last one, where the arrangement of the north-south pole within that magnetic material is also randomly arranged. So up there, I hope now you know what the domain theory of magnetism talks about. You are able to explain it. You can understand it very, very well. And just to be sure that you have been following this lesson and you understand it, you attempt this question at the end of this lesson. So we have an assignment here that you should attempt. So your assignment is here. There are just two questions. State whether a magnetic field is a scalar or a vector quantity and explain. And I think you have really explained that when you're indicating the magnetic dipoles, we use arrows. Is it a vector or a scalar quantity? Then give an explanation. Of course, you understand what a scalar quantity is and a vector quantity is. So base that on the discussion we just had. This one will score 2 marks. Then the question number 2, state the domain theory of magnetism, which was our discussion of the day. state the domain theory of magnetism. Again, you're going to score 2 marks on this. So if you are able to attempt these questions, then and get the right answers, then it means that you have followed this lesson properly and you are doing very, very well in your studies. So up to there, I have this last one for you. Quote of the day. Now let's reason out together. You are a living magnet. Do you agree with that? What you attract into your life is in harmony with your dominant thoughts. This is a quote by Brian Tracy. So you are a living magnet. So whatever you attract is actually a harmony with your dominant thoughts. Think about this so that when we meet in the next lesson, we shall be able to look at it. Now, for comments, compliments, questions, and all that, you can contact us using our Facebook page, LMTV. You can also follow us on Twitter, @elimu_KE. You can also call us on the number 0726 824 644 and SMS your questions and comments on the SMS number 40007.